Today in this module on corrosion of embedded metal, we are going to cover corrosion in prestressed concrete systems, which is most of the time it's not, there is something special about the corrosion mechanisms in prestressed concrete as compared to the conventional concrete systems. Now, first I'm going to show you a very classical illustration of prestressing. Using some of a stack of books. You can see, this is Professor Gustav Magniel's demonstration. He used to do it in class. Take a stack of books, and then press it from the side so that you can carry more load. So this is the same principle applied for prestressed concrete systems also, where you have prestressing, and there are two types of prestressed concrete systems. One is pre-tension system and the other one is post-tension system. The one on the left is a pre-tension system. There are two types of prestressed concrete systems based on the time at which the strands are stressed. If it is a pre-tension concrete system, then the strands are stressed before the concrete is cast. In the post-tension concrete system, the strands are actually stressed after the concrete has achieved its strength or after the concrete has hardened. So one on the left, which you might see these kind of bridges, most of the flyovers in the city, you might see this kind of system. Most of them are actually pre-tension concrete, and this is a typical metro on the right side. It's a typical metro bridge or elevated metro system, where you will mostly see post-tension segmental concrete construction. This time I would also like to mention, if you see an eye girder, it is not necessary that it's always like these kind of eye girders. It's not necessary that they are always pre-tension, but there could also be post-tension system. Some of the photos in the remaining of the lecture, you will see that concrete. So what is the corrosion protection strategy in the pre-tension concrete? Here you can see in this close-up, you have the black dots, which are the strands, and the gray represents the concrete. The chloride penetrates through the concrete cover and reaches the steel strand through diffusion or the typical chloride ingress processes which are also present in the conventional reinforced concrete system. And then once the chloride builds up to a sufficient level at the steel surface or the right here, you can say that the corrosion will initiate. And the pitting corrosion on strands and deformed bars are of two types, okay, or the type of corrosion which you see in the case of rebars and in the case of strands are a little different, especially the corrosion cracking patterns. So for example, in the case of typical rebar or a conventional deformed bar, like in this case, what will happen is you can see that some pits here and there, but there are also region which is not pitted much. But the point here is there is no space like in the case of strands. No space. It's a single solid bar, like this single piece, and then the only surface which is corroding is actually in contact with the concrete. So whatever the rust is formed, it will very fast exert expansive stresses onto the concrete nearby, leading to cracking, and then followed by the oozing out of this rust through the concrete cover, and then you can see that brown stains on the concrete surface. But in the case of prestressed concrete system, it's a little different. What happens is, first because of the stress, the pitting can be very significant or very localized, and you can see very severe pits, whereas some region are not at all corroding or very limited corrosion, but you can actually have severe pits which might lead to the fracture of that particular wire. Like if in this case this particular wire will fracture much earlier than the others, which might lead to structural problems. And also on top of that, whatever the rust is formed in the beginning, they will occupy these small triangular kind shape spaces between the 7 wires. Once this space is fully filled with rust, only after that the strand or the rust will actually exert pressure onto the concrete, onto the surrounding concrete. So that is the, and because of this, what will happen is there may be prolonged corrosion before you actually see some brown stains or something. So visual observation is not really a good idea when you talk about post-tension systems. So there could be, in the case of strands, there could be a delayed expansive stresses, cracking and manifestation of corrosion products. Now, and another thing which can happen in the case of post-tension or pre-stressed concrete system is that, as you see on this image here, or if you take one pitch length of the strand that's shown in this picture here, or sketch, you can see that all the 6 wires are actually getting corroded. Not only the wire, in other words, in one pitch, all the wires reaches the tops, are at the top surface, and those portions are getting corroded. So effectively, what you can see is, when you look at the cross-sectional loss over a pitch length, it is 6 times, approximately 6 times the cross-sectional loss on one wire. So effectively, you lose significantly as compared to a rebar. If it is in the case of a rebar, let's say you have a rebar like this, which is a solid bar, only the top portion will be corroding, and then this region will not be actually corroding. And the picture on the bottom left, you can see severe pitting like this here. You can see a pit form. So severe pitting, whereas some region is not at all, this region there is no corrosion at all. Now this is how, because of this, there will be significant reduction in the structural capacity, and that is a significant concern. So actually, in this case of pre-stressed concrete, we don't even want to get into the corrosion propagation phase. In fact, we want to enhance or increase the duration of the initiation phase as much as possible. That is because once it starts corroding, it becomes very dangerous in the case of pre-stressed concrete system. Now let's look at what is the strand protection strategy or system in post-tension segmental concrete. As you see in the sketch here, you have several box girders or the segmental segments. Like in this picture, you have 2 diaphragms and then 4 segments, just to show, but there will be more, just to make it more clear to understand. I have put it something like this. And then you have a tendons which run from one pillar to the other. Typical simply supported systems will be something like this. And when you look at the strand alone, each of the tendon is made of about 19, or depending on the diameter of the tendon, you will see that multiple strands are placed inside a duct, inside a plastic duct or high density polyethylene duct, which is this one. And then the space in between the strand and the duct is filled with the cementitious grout. And now this highly congested strand, and that is where the challenge is, how to get this space between the strand and the plastic duct filled with cementitious grout, properly filled. That's the biggest challenge. And then if it is not filled properly, you can actually experience significant amount of corrosion or early corrosion of the system. Now there are 2 types of tendon systems. One is internal and another one is external. The internal is when the duct or the entire tendon is inside the concrete. When the external means it's kept outside the concrete, okay? Depending on various reasons, designers might choose either to go with internal or external. So here it shows a profile, typical profile of tendons. On the top drawing, you can see it's a straight profile like this, and then it goes like that. In the bottom one, you will see a curved profile, mainly for, as you see here, it's a continuous beam system. And in the top one, typically when you have a simply supported system, you go for that kind of profile. Now, when you have this profile, the strands will not stay at the center of the duct. Okay, when you pull the strands, depending on the profile, the strand will try to occupy a shortest distance, and it will get a little bit eccentric to either one of the side of the duct. As you see here on the left image, if the strand is pulled, then it is moving towards one direction. As you see here, in both these tendons, the strands are more congested in the top portion of the duct than at the bottom portion. And in this case over here, you can see that strands are pulled toward the bottom. In this case also, it is actually at the bottom. Here it is at the top, moving towards the top. So it's not necessary that always the strands will be at the center. So because of this, what is actually happening is there is some region here like this, as I'm drawing, where you have less congested region, and the grout which you flow through that region, and then it will reach the other end. And then people generally conclude that if the grout is pumped from one end of the tendon, and if it is reaching the other end, it is actually completely filled. But that is not the right conclusion to make, because you have to really make sure that this congested region like this here is actually filled up. That is very, very important. Now, for achieving that, we have to have a very good grout and also allow enough time for the grout to flow. And the best way is, instead of pumping the grout from one end of the duct to the other end, you pick the lowermost points as per the Federal Highway Administration. This is the recommendation, especially this is based on a study conducted by Florida Department of Transportation. So as you see here, they pick the lowermost points on the profile and then try to pump in. This is the inlet. Pump the grout into the duct, and then the grout is allowed to flow upward, and through this vent it is supposed to come out, and then vents here also. So the fill in from the bottommost point, let the grout flow upward, and that's how it is supposed. That will actually ensure much better filling than filling from one end and letting the grout flow downward, etc. Now, other thing is, to prevent the void formation at the end of, or the anchorage, you can also do a little bit to prevent the void formation and entry of moisture. You can see that slight inclination of the tendon profile at the end can also. So, for example, if this is the end of the end anchorage zone, if water is coming through like this, it will never go upward like this. But in this case, you may see that water going like this. So that is this is not good, and this is a good practice to follow. Slight change in the profile. Now, nowadays you'll see that most of the most of the tendon systems, you'll have this cementitious cap like this, what is seeing on this. What is happening is, in this cement, it has an inherent property of absorbing moisture. It's not hydrophilic in nature, so it will absorb the moisture. And then if that anchorage region has sufficient moisture, definitely it is going to lead to corrosion of the strands at the near anchorage zones, and you might see strands corroding something like this in very short period of time, which is not really a good thing to happen, especially when we think that these type of structures are supposed to last for 100 years or more. Now, recently people are also practicing trying to put some kind of polymeric coating on this, waterproofing coating. But remember that these structures, when they are exposed to sunlight, these polymeric coating might actually degrade in very short period of time. Maybe a few years down the line they might degrade, unless it is very prevented or protected from sunlight. So I would say the metallic caps are the best preventive measure for these kind of systems. And on top of the metallic cap, you also should have a very good another concrete element which will protect it. You need to really take care of the anchorage zones, otherwise these structures will have severe corrosion problem in very short period of time. Now, also the joints, these are the segmental joints, the joints you can see here. So these joints usually are supposed to be filled, earlier, few decades ago, people used to go for dry joints, means there is nothing in between the two segments. You just keep the two segments together and then press it, or due to the pre-stressing action itself, and then rely on the shear keys for the resistance. However, now later on people found that it leads to severe corrosion because through this dry joint oxygen and moisture can penetrate, and which will lead to localized corrosion of the strands which are going like this. So this region will actually corrode. So to prevent that, recently people are actually using epoxy joint. So that means you put epoxy on the inside surface or the facing surface of both the segments, and then put them together and squeeze it. Because of pre-stressing, it will get squeezed, and it is supposed to fill the entire region and to prevent the entry of moisture and oxygen. It's very, very important, but we have seen if you don't really put a lot of a good amount of epoxy, it will actually lead to further leakage and corrosion later on. This is an example showing that inside the duct you can actually also have stagnant water, and it should be it's very important to make sure that these kind of things does not happen. This is not good. This is not good for the strands. So how do we prevent that? There is a design procedure where they suggest to provide a drain hole, hole on the segment for draining the water. Whatever possible water stagnation, it will drain and then let the water out. It's very important to keep these systems away from water. This is an example showing, I want to show where the water can come in. So like this is a expansion joint and or two girders. Water can come in and then enter here to this way. So this is a severe issue. So this must be avoided, and then making sure that there is a very good protection mechanism to prevent the entry of water. Okay. Now there used to be a practice of filling the duct with water before the grout is filled in. Now it definitely and then expecting that the grout will actually displace the water and prevent the formation of air voids. This was the idea for going for practicing filling the duct with water. But it is not really a good idea, because the strands might get corroded, and the type of water which you use, if it has a lot of chlorides, that might also affect. So because of this, it is not nowadays recommended to fill the duct with water before filling the grout. Okay. So you can see here, this picture was taken from one of the sites where this was actually practiced. As you see here, the color of this grout, it is not gray. It has a lot of rust, getting mixed with it. So it is not it's a proof that the strand inside has corroded to some extent. So that is something which need to be avoided. And also, we have to have, good number of inspectors and qualified persons at the site. This is a picture taken, in almost 9 years ago. But what you can see is there is no inspector at this site when the grouting was, being, the bridge was being grouted, because the grouting in essence is not given sufficient importance, and that's where the problem lies, I think. And then also the shear keys, it's leading to this. You can see an example where a shear key is lost, and it doesn't really have a good shear. This really affect the shear capacity of this. Now we generally think that the post-tension concrete bridges are having are all performing well. Why we have this feeling is mainly because most of the structures which we see around are less than 10 years old, or they are very young. So babies always look good. So that's one reason why we are having general feeling that all these post-tension structures or prestressed concrete structures are of good quality. But as time passes, we will see that this size of this yellow region is going to reduce, and then the green, white and blue, it is going to increase. So this is also a pie chart here. Okay, so let us not judge the long-term performance of these structures based on the short-term performance. It's very important to understand this, and we really have to do things so that these young structures will actually last as long as they are desired to last. So the protection of strand is from corrosion is very, very important. So this is a bar chart showing the premature corrosion on prestressed concrete bridge, post-tension bridges. So the numbers in the parenthesis shows the number of years before they exhibited or showed corrosion. Now, what are the issues? Mainly the tendons are inadequately grouted, and hence they corrode prematurely. In this picture here, this bridge actually failed after the tendons were refilled with grout, and in very short period, you can see here, within about 15 years they started experiencing corrosion, which is not at all expected in these kind of bridges which are designed for 100+ years. Now, where is the corrosion actually happening? So you see the profile here, and then what is happening is the cement in the grout will segregate. Cement will move downward and water will move upward. So cement will move downward, water will move upward, and then basically it segregates, and then you see lot of bleed water will form at the top portion of the tendon, like it is shown in this close-up, and then eventually that bleed water will evaporate. So you can see this unshaded or the white region is supposed to be filled with this white region is supposed to be filled with grout, but it is not. So that will lead to additional problem. This is another bridge where you can see a vertical tendon, like in this pillar here, where this portion here is not at all grouted. So that's also leading to severe corrosion, as it was visible in about 8 years. The strand system completely corroded, which is again very early corrosion. Other kind of problems which can be observed is the broken ducts. If the plastic is of not high quality, broken duct, and then a lot of voids present, and then water stagnation, and then a lot even there are regions where there is no grout at all. This is a picture taken from the center span, but there is no very clearly indication that there was no grout reached at this location. So and then this is another failure which happened in just 33 years due to poor grouting. This is another demonstration of poor grouting being used. As you see in this bridge here, on this end you can see a semicircular region of grout. If the tendon was completely filled, the tendon goes like this in a horizontal tendon on this girder, the pier cap. If it is not filled properly, you will see this semicircular or partially filled. If it is properly filled, this grout should be a perfect circle, and which is not visible. It's very clear that the grout used in this. What is the problem with this is that after some time, as you see here, if there are regions with no grout and with grout, the top portion of this grout, this indicated by this red line, horizontal red line, the top portion will get very easily carbonated. Now when you have carbonation like that, and chlorides can enter, and CO2 can also enter through this, and it will carbonate this region. Now you have a strand which is passing through a good grout, and it is exposed to a highly carbonated grout. Now that leads to accelerated corrosion of the strands. And this is also an example picture here which says that partially filled region. And in this picture, if you look very carefully, you can see that the top portion is actually showing more corrosion than the bottom portion. These are all evidences showing that there is severe strand corrosion due to inadequate grouting. Now in the market today, due to the significant void formation, people have worked on developing better quality grouts. However, even better quality means grouts which can actually fill the tendons much better. But even in some of those grouts, we see a new type of problem, which is the soft grout formation, where the inert materials which are used in these grouts were floating, and it forms this soft grout as you see here, very porous in nature, and which can actually absorb the moisture and keep it there. So it's like froth in a coffee cup, on top of the coffee, very porous, very low strength, which can absorb moisture, keep it there, and then lead to corrosion of the strand. Now the tendons are really the backbone of post-tension systems, and it's very, very essential to make sure that they are protected well from corrosion. Otherwise we will have severe corrosion related issues. So we looked at pre-stressed concrete system, and they can be vulnerable. How they corrode, we should not look at rely on the visual inspection or visual manifestation of the the rust on the concrete surface. That is not a good idea. And that in the pre-tension and post-tension concrete systems, the corrosion mechanisms are different. Rather, the mechanism leading to corrosion is different. In the case of pre-tension system, it's mainly through the chloride diffusion through the cover, whereas in the post-tension system, it's the grout, inadequate filling or inadequate grouting is something which relates to which leads to premature corrosion. And these are the references, a list of all the references used in this presentation. Okay.